Hi, this is a video for compiler design, COMP442 and 6421. This is for week 6. This is the last video where we're going to talk about syntax-directed translation. In this video, I'm going to talk about how you can use a syntax-directed translation to build an abstract syntax tree from a top-down parse. So this is, again, going to use many of the concepts that were covered before. So it's basically building incrementally on things that we saw before in syntax-directed translation concepts. So if you jump right to this video, it's probably some things that you're not going to understand. So I invite you to not jump here, but listen to all the videos before this one that is all in the series of 4 videos talking about the parsing. The last 4 videos talking about how to build eventually an abstract syntax tree using syntax-directed translation. So what is an abstract syntax tree? So abstract syntax tree, or AST, is a tree representation of the abstract syntactical structure of your source code. Now, why is it called abstract? Well, the thing is that there is in your source code, or as you traverse your parse tree, as you're doing the parse, you're encountering some symbols, like, for example, semicolon or open close parenthesis, all kinds of symbols which, after you have parsed them, they become somehow useless. Okay? So what you want to, they don't convey any meaning in the program after you have the tree. So they are superfluous after you have formed the tree. So that's why if you want to have something that's more efficient, a representation, then you should remove these superfluous information. Another thing also that's going to happen is that, as we saw repeatedly now, when you have removed the ambiguities in your grammar, including the left recursions, it has somehow mangled your tree by separating many right-hand sides, some right-hand sides across different right-hand sides. Thus, for example, creating the fact that if you have a plus operation, then the left operand of the plus is now suddenly in a sibling subtree of the subtree where the plus operation is happening. So of course, you don't want to have this. If you want to do things more efficiently as you are, for example, analyzing your code and generating your code later, you want to have both of the operands of every operator on a single subtree. You want it so that you have a certain syntactical construct that all the information about this construct is stored in the same, in its own subtree. Okay. So that's what an abstract syntax tree would also be, which is, of course, a definite advantage over the parse tree, especially if you had to remove ambiguities and transform your grammar. So your abstract syntax tree is going to somehow put everything together back how it was before we actually had removed the ambiguities from the grammar. So then each node in the tree represents a syntactical construct. So for example, you will have a node for a class. You will have a node for a function definition. You will have a node for a variable declaration. So these are some important building blocks of your programming language that are, of course, going to be important when you want to analyze the semantics of the programming language, for example, to build symbol tables and eventually to construct a code for your, to translate this tree into a program, an executable program. So you need to have this structure where each syntactical element is, or building blocks is stored in one single subtree. So as I mentioned earlier, syntax is abstract because it makes abstraction of some details that are superfluous, such as, for example, the semicolons, the parentheses, and so on. These are all superfluous information that you don't need to have. So that these would actually be part of what is called the concrete syntax of the language. So we use these superfluous symbols so as to make it clear in the input program how things are, for example, grouped together or separated. For example, we use semicolon to separate every statement from one another. If you have a list of parameters for a function, we use parentheses. These are all syntactical sugar that we call in terms of programming language design terminology. This is syntactical sugar you add to make the expression of your programs more easy to understand from a human perspective. So this is your concrete syntax. Eventually, as you have processed the initial programming language that the program that you are processing, you don't need this syntactical sugar, so you get rid of it to build the abstract syntax tree. So that's what is distinguishing the abstract syntax tree from a concrete syntax tree. So your parse tree, as we saw before, was in fact a concrete syntax tree. What we want to have at this point is an abstract syntax tree. So then once you have this abstract syntax tree that is built, then you would be able to use some algorithm to actually traverse the tree and do some further processing. For example, building the symbol tables in one step, and one step further, you do, for example, the type analysis and the binding between symbols that are used in the program. And so on and so forth, and then eventually the generation of the code. It's all going to be done by further successive traversal of the abstract syntax tree and building new information, such as symbol table and eventually code. Okay. So we'll see later in next week how you can actually use what is called the visitor pattern to actually do tree traversal and then separate each of your phases, the subsequent phases of analysis and code generation by using different visitors. Okay. There's other ways to do this, but the visitor pattern is a very extremely interesting pattern that is ideal for that kind of processing. So what is the goal of having an abstract syntax tree? So first of all, you want to aggregate information that is gathered during the parse to gather all the information that is related to a specific whole syntactical construct. So for example, you might have encountered a variable declaration, which can include the type of the variable, the name of the variable, and then potentially the list of dimensions if this variable happens to be an array. So eventually that would all be gathered in an entire tree of the program. So what you want to do is to actually create nodes that represent all of this information gathered, and that eventually you're going to have at the end of the processing of this tree, you're going to end up returning or having this entire concept represented by the node that is the root node of this subtree that represents this variable declaration. And you're going to have same thing for a statement or an expression, a function header, a class declaration. So every construct, syntactical construct, is going to have its own subtree, specific subtree that is going to be used, kind of subtree that's going to be used to represent syntactical constructs of this form. Okay. So this is about aggregation of information. That is all the information you need to know about a specific syntactical construct as expressed in the language. So eventually what you want to have is that you want to have a root node of the entire program that actually contains information of all the program. And eventually, for example, also what's interesting is that, for example, a program can have a list of classes. For example, you can have something like this. So you have your program. And then, for example, one of your things you can have a program is, let's say, a class list. And then you would have one class subtree for every of the classes that you have in this program. And then, for example, for this class here, you may actually aggregate all the information about all the members that are in this class. Thus, for example, enabling you to create a symbol table for this class, and a symbol table for this class, and a symbol table for this class, by essentially traversing all the children of this class here that would contain subtrees for every variable or every member that is being declared inside of this class. Okay. So by traversing this subtree here and aggregating information, you can eventually create the symbol table for this particular class. And then you do the same for every class. Okay. So you see that by having a separate subtree for every concept, then you can further do the processing of everything that's related to this concept, because everything is in the same subtree, which you can then traverse and aggregate information from. Eventually, what we're going to do is that we're going to use, as I said, the visitor pattern to repeatedly traverse this tree. And then for each of the different processing steps, then we will have a different visitor that is going to do one traversal of the tree for every sub-step in the further processing that we're going to have eventually. So then in your abstract syntax tree, at the leaves of the tree is in fine-grained information that you have about the atomic concepts, as we will see later. That's where you actually gather the information from the source, which is generally speaking in the tokens that you have, that you are parsing. And then the intermediate nodes, for example, like class here, represent a high-level construct created by the aggregation of different branches or subtrees that are children of this node here. Okay. And then at the root of your tree is a single node that actually represents the entire program. So one of the things when you start, so you have to analyze it, you have to create this abstract syntax tree data structure. That's what, for example, you saw in COMP442 when you analyze what is a data structure, what you need, what are the requirements for your data structure, in terms of what kind of processing are you going to have to do with this data structure, which tells you what is the form of this data structure. Okay. That's what I'm going to be doing here. So first of all, the abstract syntax tree structure is constructed from the bottom up. So eventually you're going to create nodes that are going to be leaf nodes. These are nodes that by definition don't have any children. Okay. They will be themselves children of a parent. So right away here, you have the possibility that, of course, that the child node needs to know who is their parent. So there needs to be a link between the node, which is the child, and the parent. Plus, if you want to loop over all the children, then these children needs to be organized in some kind of list. So the minimal requirement for the relationships between the children is that they be organized in a forward linked list. Okay, so there should be one link between the leftmost child to its right sibling. Then the right sibling has a link to the right sibling, and so on and so forth. So basically, you have a forward list. And each of, if you want, if, for example, it might be possible also that when you're processing a certain child, that maybe this child want to be able to traverse the list of all the children. So that means that every child should also contain a reference to the first child in the list if you want to be able to traverse the list as you're processing one child. So that's basically expressing the relationships, some of the relationships between nodes. A node contains a pointer to their, or a reference to their parent, and then has a reference to their right sibling, as well as a reference to their first leftmost sibling. Okay, so other discussions. Some nodes will require a fixed number of children. So for example, if you have an operator, say you have the plus operator clearly has two operands, which will be eventually their children. If you have the unary plus operator, it's an operator that has always only one operand, so it has only one child. The if then else statement is clearly something that has always three children: the conditional part, and then the else, the then part, which is a list of statements, and then the else part, which is a list of statements. So it has three children. There are also some nodes which have a variable number of children. Let's say you have a parameter list. When you define a function has a list of parameters, which can be from 0 to any number of parameters. Then you have the parameter list is a node that has from 0 to n number of children. Okay. So there's no predefined requirement as to how many children there should be. So you should be able to have from 0 to n children in such a data structure. Eventually, what we're going to have to do is to do depth first search. So this algorithm, if you analyze it, then it tells you what also is the requirements. Because if you want to do depth first search, you need to be able, for example, to point to your parent. As you went down into, of course, every parent must have a list list of their children, especially the leftmost children, because that's how depth first search is working. Start at a node, you go through the list of all the children starting from the left. So you need to have a link to the leftmost children. And after you finish traversing a subtree, then you need to be able to come back. So you need to have also links to the parents. So every node needs to have a link to their parent. So a parent needs to have a link to their leftmost child, and every node needs to have a link to their parent. Then also, as you want to do depth first search, you want to list, to be able to go over the list of siblings in a subtree. So you need to have, as I said before, links between the left child and the right child going in this direction, from the left to the right. And also that each child needs to have a reference to their leftmost sibling. So that's what, if you analyze depth first search and its requirements, that's what it tells you. So eventually we end up having a node like this. By the way, these figures here are from the Fisher book. Reference here, just to make sure if you want to see where this is coming from. This is coming from the book Fisher, Citron, LeBlanc, or LeBlanc. So much of what I'm describing in this slide set and the previous slide set is also from Fisher and LeBlanc, Citron. So this is where you would see this figure, for example. So every node in this data structure needs to have a link to their parent. It also, each node needs to have a link to their leftmost child, possibly, and then needs to have a link to their right sibling. And then that allows you to create any kind of form of abstract syntax tree from this functionality. Of course, if the node is actually a leaf node, then of course what would happen is that they would not have a child, or their child would be set to null. Their leftmost child would be set to null. Of course, that should be possible also. Then eventually what you want to do is to be able to create the nodes. So in this case here, it's saying that you could have a factory method. For those of you who know their design patterns, factory method is essentially a class that you call to create something which is of an abstract class that has subclasses, and you're actually creating something of the type of the abstract class and returning one object of one of the subtypes. Okay. So eventually you would be calling this make node factory method, and then depending on what parameter you pass to it, then it would be creating one of the different kinds or subkinds of nodes. One thing very important that you should understand is that you will have to, you should not have only one type of node. Yes, you will have the super type node, and all your nodes will be of the same super kind, which is node, but then you need to have one subkind of node for every kind of subtree or syntactical construct that you will eventually generate a tree for. Okay. So yes, you're going to have a generic node class, but every node will be of a separate subkind of node. And that's what actually your factory method would do. When you call it, it returns, yes, a node, but it's always a subkind of node. Okay. So for example, if you are at the leaf of a tree and you see an integer literal, then you call make node to create an integer literal node. So yes, it's a node, but it contains information by its type as to what kind of node that is. That's of course going to be very useful as you traverse the tree, depending on what kind of node that you see. When you use the visitor pattern, the visitor pattern is going to do different actions depending on what kind or type of node that it's actually encountering. Okay. So it's important that every of your node have different subkinds of the node super type. So if you see an ID at the leaf, then you create an ID node. If you see an integer, it's going to be an integer literal node. If you see an if then else node, then it's going to have a different shape, and it's going to have a different type. So for every different kinds of subtrees you're going to eventually create, you have a different subkind of node. I'm going to cover, that's the last thing I'm going to cover when we see toward the end of this lecture. I'm going to list every different kinds of possible subtrees and subkinds of nodes. Then here, I'm not going to go into explain all the details here, but the thing is that you need to have some functions that enable you. For example, here this function make siblings. What it does is actually it enables you to somehow add a sibling in the list of siblings that you already have. Okay. It enables also you to possibly take a list of siblings and then graft it into another list of siblings when that could be necessary. Okay. So essentially here, make siblings is to add to a pre-existing list of siblings as you are finding the next sibling, as you are generating your different sub-branches, as you're processing, for example, this subtree here. Okay. So every time you will go to a next sibling, you will call the make sibling to actually link this new sibling with the pre-existing list of siblings you already had. That's what this make siblings function doing. Then you have the function adopt children that you will use to actually tell, for example, this node here to adopt this list of siblings that you have processed before. And then eventually what you want to do is to call, when you want to create an entire subtree, then you will call make family of, in this case, class list. So make family of class list, and then you would give it the list of siblings. Then it would actually eventually link each sibling together, and then will tell this node that you've created here to actually adopt these linked children, thus creating, assembling this whole subtree together here into a single subtree below this new link that you've just created. And then for each of the different kinds of subtrees, then you would have a different up here. So here up would be the class list. Then up, if you are here, up would be class. Then you would have an make family for statement, make family for a while loop, make family for a variable declaration, make family for list of parameters, and so on and so forth. For every different kind of sub-syntactical construct, you should have be able to call make family to create such a subtree. So for example, here you have an assignment. An assignment is a variable which is assigned to an expression. So that's the subtree for assignment, which has two subtrees. Plus operation has two operands, which are two subtrees which represent their expressions. An if statement, as we saw before, if statement has the predicate part, the then alternative, and then the else alternative. The while statement has a predicate and then a loop body. Eventually, the loop body is going to be composed of a statement block. So you would have a statement block that would be here. Okay. So you see here that eventually you're going to be calling this make family for assign, make family for plus, make family for if, make family for while. And depending on what kind of node you want to create, then you're going to have to pass it each of the children of this actual concept. Now you see here that this function, essentially this is defined as a variadic function. Now you may realize, of course, that not very many programming languages allow variadic implementation of variadic functions. If you don't, then basically what you need to do is to create one sub-function for every different kind of tree that you are going to create. Here, the example that this book is using is slightly more complex than our example that we used to have. I chose to go in this direction just to show you a broader perspective. Because if I will just continue here with the same example, the scope of this example about expressions that we used to have before is quite limited. So here I want to broaden your perspective here by using this more broad example. So essentially here, what you have is that it's a program is a list of statements. Okay, so a statement can be an assignment statement, or an if statement with an else, an if statement with no else, a while statement, or a statement block. Okay. Then here you have a rules that are defining a list of statements. And then, of course, these statements are themselves using expressions, which uses terms and so on and so forth. Okay. Now, it's important here to understand that this grammar has not been transformed to be an LL1 grammar. Yes, but that's not the point. We want to basically have an example here that is easier to follow by not having been mangled by the transformation of the grammar. Okay. So then you will see here that this example relates very much to what I actually explained in the previous two videos, where you actually insert semantic actions inside of the right-hand sides of the rules. Okay. So essentially here, I have my grammar rules here, which are in black. And then I actually have inserted here, I say I, but it's an example again taken from Fisher book. So they essentially here, these are semantic actions that are being inserted in the processing steps, or the right-hand sides of your grammar. So after you finished parsing an expression of this kind, then you actually call my family, make family of an assignment statement, where you pass it the subtree of representing the variable that is on the left-hand side of the equal, and you graft it, become a child of assign, and then the expression that defines the right-hand side of the operand of the equal becomes the second child of the assignment subtree. So here, essentially, you are crafting by using making a call to make family. You are creating essentially this kind of subtree here. Okay. And I remind you that make family is actually assembling each of the children together by using make sibling, creating the assigned node by using make node, and then essentially calling adopt children on the assembled list of siblings, and adopting this list of sibling by the assigned node. Okay. So here, this is a very specific way of doing it. It's just to explain what is the concepts. There's a lot of different ways you can do that. Okay. I'm not saying that you have to do exactly this way, but the end result must be the same, that you are essentially creating a subtree, you have children, and then you create a new node that needs to adopt these children, and then you create a subtree, and you return it, which is then passed as a child to a node further up the tree, and so on and so forth. Okay, so here you see that all that I've highlighted in yellow, all the calls to make family, that's basically on your way back when you traverse the tree. So yeah, I'm going here and I go and I process each of the children. The make family is essentially called when I finish parsing the last child of my class list. Then this is where I will actually call make family by creating this node, making it adopt all these nodes in the list I have just went over. They are now being adopted, and I create this subtree, and now I have a subtree for my class list. Okay. So these make family trees are those make family semantic actions are those that are called on my way back when I actually go back to the parent node when I do my depth first search. The make siblings function would be called after I have actually finished traversing a subtree of a child. Then As soon as I go to the next one, then I would actually connect this child with this other child here. And when I connect here, when I come here, I connect this child with this child here, which is already connected with this child here. So the make siblings is actually assembling the list of siblings. And then, of course, at the leaves of the tree, when I gather the information at the leaves, and that's what actually I'm calling make node to create the nodes. And of course, I'm calling make node also when I'm coming back to as a part of creating of calling make family. So make node is called anytime a node needs to be created. So let's see an example here of a program that is valid according to this grammar. So that's the program I have here. So it's an if statement that contains a while statement that contains an assignment statement or two assignment statements, and so on and so forth. So you see, this is the concrete syntax tree that I would get if I do a parse using the rules of this grammar as they are defined in the grammar itself. Then, of course, what's happening here, or most particularly what would be happening if you would remove, for example, the left recursions, is that here you see that the two operands of my plus here are on the same subtree. That's fine. However, if you would have removed the left recursion, then I would have my operands that are scattered over different siblings across the same subtree. Eventually, if I construct my abstract syntax tree in the way I've just described, I'm going to end up having a tree like this. And then in our case, even if we had removed the left recursions and ambiguities and so on, if we generate the abstract syntax tree in the way I've described before, then you would end up having back both, for example, of the operands of your plus on the same subtree. Okay, which is, of course, one of the very important goals you want to achieve when you parse using a top-down parse, which required that you remove the left recursions. So that's the kind of tree that we're going to have after we process. We do the syntax-directed translation that is constructing the abstract syntax tree in the way I've just described. So going in more abstract description. So here it's describing, abstractly, what is the terminology that we are using here? What is abstractly, what is it that we are doing? Okay, what are the concepts involved? So essentially here we're assembling a notion of a semantic concept. Okay, so a semantic concept is a building block of the meaning of a program. So a program is a composition of different sub-concepts. For example, in this program, I have different classes. So there are different classes that are used in this program. Each of these classes each have, for example, different data members that are local to this class, that are not accessible necessarily by the other across classes. And each of these classes has member functions. Each of the member functions inside actually has variable declarations that are local to these functions. But these are all increasingly detailed semantic information that are very often encapsulated into one another. Okay. So that's what you want to express here. So you want to define these semantic concepts, so you would eventually have some atomic semantic concepts that will eventually be represented by abstract syntax tree leaf nodes. That's where you will get the atomic concepts that are not composed of other concepts, such as, for example, an identifier is an atomic concept that is not defined by other atomic concepts. For example, a literal value, an identifier, that's all atomic concepts. Then going up the tree, you have composite concepts. These represent higher level concepts that aggregate and subordinate concepts, not necessarily atomic concepts. Composite concept is a concept, a semantic concept that includes other concepts. So for example, you have a program that is a semantic concept that contains or uses the notion of a class list. And inside the class list, you have a composite concepts, which are the classes. Okay. So these are the classes are the composite concepts that are used by the class list to define what is a specific class list. The composite concepts are represented by abstract syntax trees, subtrees, which have n AST subtrees as children, which happen to be their subordinate concepts. So subordinate concepts of class list is a list of class composite concepts. So then for each of the different kinds of semantic constructs that you have or syntactic constructs that you have in your language, then you would have a specific composite concept. For example, the classes, function definitions, the statements, the expressions, variable declarations, and so on and so forth. The general procedure is that, so as you reach a leaf node as you parse, then you would actually get, you have reached an atomic concept. So when you reach an atomic concept, then you somehow have reached a leaf in your tree, which is represented by a certain token that you have identified. So in this token, there will be some information that you will actually store in the node itself. So for example, if it's an ID token that you have identified, then the name of this ID would actually be stored inside of the AST node that you are creating. Of course, what you can do is to put the token itself inside of the node. Okay. Which would be handy because further down the road, you want, for example, to be able to, when we'll traverse the tree to generate the abstract, the symbol tables, if there are some semantic errors, for example, type errors, then we still want to be able to identify, for example, a certain ID. There's a certain semantic error using a certain ID, which is the wrong type in a certain expression. We want to be able to say where this ID was encountered in the program, which is information that you actually have stored inside of the token itself. So the token can actually be somehow the data element, that atomic data element that is stored in your atomic concept node. So you get this information from the token, and then you create this node. You put this semantic information inside of the node, and then you push this node onto the stack. Then after you've reached, you've completed the parsing or the traversal of all the siblings in a list of siblings of a particular composite concept, then you actually create the node that represents this composite concept. You graft all its children to it, and then eventually it's gonna, by extension, by transition, is going to now contain all the information that is contained in all the nodes that are below it. Thus, there is access to all this information through this node here. Okay, so that's how the information has been aggregated. Then once you have created this node here, then you push it on the stack. So that now becomes a child of another node upwards, so that you can eventually take this child and graft it onto this one, then take this one and then push it on the stack. Okay. So here, I'm gonna very quickly here go over this because we saw this twice before. So I'm just basically here, what it's doing is showing the same example that we shown in 2 videos before that, where I explain how you actually can do attribute migrations, attribute migration using a recursive descent predictive parser. If you remember in the example before, I was using the notion of semantic record in an abstract way. Here, I'm just basically having exactly the same example, but showing that I actually have abstract syntax tree nodes as my semantic records that are being constructed by the operation of my parsing functions. Okay. So it's exactly the same thing. In the previous example, it was semantic records, very abstract. Here, it's very much more concrete. It's nodes of an abstract syntax tree that I'm creating as a result of my executing my parsing functions. So here I'm creating an AST node that I name ES, and then this is an empty node that I'm creating, and I'm actually passing this node to my function E. Of course, my function E, what it's going to do is that it's going to create a subtree for an E node. And then when this function E returns, then I will have this ES here that's going to be representing the entire subtree that was created as a result of having called my E parsing function. Then, of course, when I call my E function here, it receives this ES, which is at this point, this empty abstract syntax tree node that I have created and passed here. Again, very important you understand, you remember that this is passed as reference. Okay. Then for each of my different subtrees for the E node, then here I will eventually call T and E prime. So T and E prime themselves are, I will call them to actually create other subtrees. So eventually here, there is 2 subtrees that I'm going to be creating as I am parsing the E, the T subtree and the E prime subtree. Then eventually I'm going to pass the empty TS to T, which is then going to be processed by T and generate the subtree for the T. Then this subtree for the T is going to be passed to as a parameter to my E prime function. Remember that this TS is now going to contain the subtree that eventually has the left operand of my plus operation. Which then is passed as an inherited attribute to the E prime. Okay, so again, it's exactly the same concept as we saw before, except that here the semantic information that I'm processing is abstract syntax tree nodes. Some of these nodes actually is the parent node of an entire subtree. Passing nodes around, some of them are atomic nodes, some of them are a parent node of an entire subtree. And eventually I'm constructing each of the subtrees. And then when it comes back, it graphs subtrees together. For example, here I'm having a call to make family to actually graft the entire, the left operand of the plus, which is the inherited attribute from the T, and the right operand of the plus, which is the synthesized attribute of an E prime. And I'm creating a plus node, and I'm electing these 2 nodes here as siblings of the plus node. Okay. Then I'm actually returning this plus node to the calling function, and then it goes up and up and up in the tree. Okay. So this is how it goes for this example. So, and you see that in the F function, this is where actually I come to the leaf nodes, where I'm actually identifying my IDs, and I'm encapsulating this ID information inside of a leaf of my tree. And then this ID is eventually passed around as a synthesized attribute and inherited attributes, and eventually gets to be a parameter of one of the operations. In which case it gets grafted as a child of the operation. in question. So again, what's going to happen here is I'm going to essentially, this is my parse tree. That's the trace of my parsing operation that is happening when I parse A plus B times C. And this is representing what's happening with all of my nodes here, all my tree nodes that I'm creating here. I'm creating this node that represents this ID here. This ID node gets from here to here to here to here, eventually to here and here. And then it is actually passed to the E prime function, which eventually will take this left operand of the plus and then this right operand of the plus, and then it's going to graft the left operand of the plus, which is the A node here, with this node here, which happens to be the top node of my times operation, which I have processed at this level here. Okay. So eventually, from this entire very ugly, I might say, tree, I'm going to create this very neat and simple tree, which is my abstract syntax tree, which is essentially the same, representing the same information as I had in this parse tree or concrete tree, concrete syntax tree. Of course, you would realize that when eventually I want to traverse my tree to do some more processing and code generation, this one is much, much more useful than this one here. I could eventually have created a tree data structure that would literally represent this whole tree here, but it would be not so much useful because of its it's been mangled by the operations of removing the ambiguities and left recursions. So I much rather would have a simple tree like this. This next example is showing if you want to use an explicit stack by doing the recursiveness and predictive parsing method. So here, instead of passing the parameters using, instead of doing the attribute migration by passing parameters to your functions, you're actually using an explicit stack. So here you're creating your node, just like we had in the previous pseudocode I've shown you. You're creating this node ES, which is an empty node at this point. So I'm basically pushing this node onto my semantic stack. Remember when I explained in the previous video that when you're doing the table-driven top-down parser, if you want to do abstract, if you want to do syntax-directed translation, you have to implement a semantic stack. So in this case, this stack I have here in my recursive descent predictive parser that implements the syntax-directed translation, this stack here is my semantic stack. Okay. In the previous method I've shown you, there is a semantic stack. The semantic stack is in fact the function called stack of the runtime system that is running the program. Here I'm doing just the same, except I'm having an explicitly programmed stack that is part of my program rather than being part of the execution of the runtimes, execution of this program by the runtime system. So push my node, my empty node ES on the semantic stack. Of course, when I come into my E function here, first thing it will do is to pop this ES from the stack, and then eventually it's going to process this ES here by doing this processing here and eventually pushing the ES onto the stack. Okay, so it popped the empty ES here, and do some processing and then push back the completed subtree for the entire expression E. Okay. Of course, here I'm using this TE prime again, so it needs a node for the operation of the T function, and then a node for the operation of the E prime function for the left and right operands, and so on and so forth. So basically, I'm pushing them on the stack empty. They're being processed by T and E prime here by popping them and filling them up and so on by the operation and by calling other functions and so on and so forth. Okay. Exactly like I would just describe before, except that now it's using an explicit semantic stack. So it's essentially exactly the same thing that it's doing, which is also exactly what it was doing when I explained how to do the syntax-directed translation for the table-driven top-down predictive parser in the previous video. So now, then here I finished this discussion by showing you an example grammar. It's not the same grammar that you have. It's not exactly the same grammar that you have in the project, but it's very, very similar. Okay. For example, a program is a list of classes, followed by a list of function definitions, followed by the program keyword, followed by a function body. So you have class declaration is defined as this here, function definition, and then eventually you have inside of your function body, you have a list of variable declarations followed by a list of statements. This is your variable declaration. This is all the different kinds of statements and so on and so forth. And you see that it looks very much like the grammar that you have in your assignment now. However, of course, I've changed some things so that people don't are not tempted from copying from code from their fellow students in past years. So not exactly the same as your grammar, but it's extremely similar. Then what you need to do is to define what are all the different composite concepts, okay? Composite semantic concepts. First of all, the one on top, of course, is your program. So you need to have a kind of node, which is the, for example, prog node. So what is a prog node? A prog node has three children: a class list, a function definition list, and a statement block, which is the statement block of the program function, or in your case, the main function. Okay. So these, you see here that these are composite concepts. Okay. So the program node or composite concept has three subordinate composite concepts. So eventually you're going to have to be able to create a node of type prog, and then eventually this node of type prog is going to have always three different children. Okay. So that's what you want to do. That's what I'm showing here by the exercise here, is to identify what are all the different possible concepts, semantic concepts that I should have, which is going to determine all the different sub-kind of nodes that I should be able to create, and eventually create a subtree for each of them by grafting each of the children that are appropriate to this specific kind of composite concept. So program has a class list composite subordinate concept. So class list is actually a composite concept that is essentially a list of classes. Okay. It's important here that you're not tempted by just basically say that I'm gonna not have a class list. I'm basically gonna have here this list at this level here. Because if you put the list at this level here, then you're not going to be able to determine where is the end of this sublist in the list of children. Okay, so it's important that you make it that you keep things separate. So a class list is something that is different, semantically speaking, than a list of functions. The list of classes and the list of functions, each of the children of both of these things are not of the same kind. So you should not put them at the same level in the tree. They should not be siblings in the tree. Okay. If there are class declarations, they should be only siblings with other class declarations. They should not be siblings of function definition list. So these here should not be siblings with one another. That's what I'm saying. Because if you want to go, if you're at this level here and you want to know what is the list of classes, then you would have no way of knowing when is the list of classes ending and when the list of function is starting. Okay, that's the reason why you want to have this level of abstraction here that is different. That's a very important concept here. Because if you omit this step, then it's not going to work. Okay, so then I have my class list composite concept here, and then it raises the need to have this subordinate concept that I need to define further. So all the triangles here are subordinate concepts that are defined by another subtree defining a composite concept. Then my function definition list subordinate concept is defined by this kind of subtree here. So here I'm created another sub kind of node. So at this point I have nodes that I can create. The nodes can be either a prog node or a class list node or a function and definition list node. Basically you go down in the concepts until you have defined all the different possible kinds of semantic concepts in your language. Okay. That will tell you what are all the sub kinds of nodes that you need to be able to create when you create your tree. Not going to go into all of them here, but let's go into some of them. So a class declaration. So you have the identifier of the class. Then you have the list inheritance list that this class inherits from. Then you have the list of members of this class. Okay. The inheritance list is either empty. You have to, sometimes you need to have the possibility that a node can actually be an empty node if it's absent. In most cases, that's represent when you have a list, which can be empty, such as the inheritance list of a class. So, and if it is not empty, then it's essentially an inheritance list, which is one of your composite concepts, semantic concepts. And then this inheritance list is essentially a list of IDs, which these IDs are now atomic concepts, which don't have children. So you see my atomic concepts are actually circles. My composite concepts are ellipses. And then my subordinate concepts are triangles. Okay. Then you can have a function definition where the return type of the function definition is the first child according to this grammar, which is different from what we have in our specific grammar this year. So type, and then scope specification is depending if the function is a free function or a member function. Scope specification would be, if it's a free function, would be empty, and if it's a member function, would be the ID that represents the class to which this function definition is a member of. And then you have the name of the function, and then you have the list of parameters to this function. And then you have a statement block that defines the body of this function. And so on and so forth. So if you go down, you go down the tree, then you define what is a member declaration. It's either a variable declaration or a function declaration. Where if you have a list of parameters, functional, formal parameters of a function, it's a type, an ID, and possibly a list of dimensions, and so on and so forth. So here you see that I'm going down somehow in the tree that defines what are all these sub-semantic concepts that are represented by each of the syntactical constructs of my programming language. And eventually I have my statements. The if statement has 3 children. The assignment statement has 2 children. And then in this case, there was a for statement. In our case, you would be having a while. Then you have the get statement, the put statement, the return statement, and so on and so forth. So these are all different kinds of sub-node types that I would be that would have to be able to create as I create my AST. Then eventually you're getting to the expressions and arithmetic expressions and so on and so forth, and the term and the factor and so on and so forth. Here it does not go into all the details of the grammar. It's just basically keeping at a certain level of abstraction here. So this is actually how you define. You have to analyze, build all your semantic concepts here and identify them all so that you know what are all the different kinds of nodes that you will eventually be able to create, and what is somehow the shape or the arity, if you want, of or the number of children that each of these semantic concepts will have as subordinate concepts, which will tell you when you want to create a tree of this kind, how many children you need to actually graft or elect as children of this parent node that you're creating. To create a subtree, for example, of this kind, you need to have 2 children. If you want to create a subtree of, for example, a for statement would need to have 1, 2, 3, 4, 5, 6 different children. So for each of these different concepts, you define what is the sub kind of node, which is the parent node of this concept, and then define the structure, basically how many children it actually needs to have in order to define everything in this semantic concept. So that's eventually what you need to do. That's the final step of what you need to do in order to construct the abstract syntax tree. So I would invite you to go also to the lab. In the lab, they will also show you how to, because one of the things I'm asking you to do in assignment number 2 is to be able to output to a file your tree. In the lab, I've asked them to, the lab instructors, to explain to you how you can actually use the dot language of the GraphViz library, which allows you to express a graph in a text format so that you can actually use the GraphViz tool to actually visualize your tree. So that as you do your parse, as you do the syntax-directed translation, you can call some functions, semantic actions that are outputting a part of the tree to this text file, so that eventually the text file is being written as you do the parse, and eventually it actually represents your entire graph or tree inside of this text file, which you can then visualize using the GraphViz tools that you can find online. That enables you to actually, anytime you call your compiler on a certain program, to have this graphical representation, this text representation of your graph that represents your tree, and that you can actually see this tree. It becomes very handy further down the road. If things are going wrong, at least you can see the tree of your program. If something is going wrong, you can see where it actually went wrong. Okay. So anytime I'm asking you in one of the assignments to output something, sometimes it appears that it's not necessary. It is very well thought of. Believe me, if I'm asking you to output something, it's because it's going to be useful to you in doing these assignments. Okay. Well, that's it for this video. Thank you.